This is lab for oscillations. So for this lab, we had to analyze the motion of a spring mass system in which the mass swings in an arc while oscillating using tracker. And then we created a computational model, and then we proceeded to compare those two models. So the purpose of this lab is to determine if the model follows the energy principle. And the result was that the total energy of the system remains at zero, which demonstrates the energy principle. So some of the fundamental principles are Newton's second law, which basically means that the change in momentum of a system is proportional to the net force applied. And we also use the position and velocity update formulas. And then another important principle is the energy principle, which basically means that the change in energy is equal to the work done by the surroundings and the thermal energy that is exchanged with the surroundings, which basically means that total energy remains the same as energy is neither created or destroyed. And then some of the formulas we're using is kinetic energy is equal to 1/2 mv squared, and gravitational potential energy is equal to mg delta h, and the spring potential energy is equal to 1/2 ks squared. So these are the initial conditions. So the mass is 0.402 kilograms, and the L is 0.7 meters. And the initial position was negative 0.121, negative 0.621, 0 meters, and the initial velocity is 0. And the system is the spring, the mass, and the earth, and the surroundings is nothing. So this is the observed position. So the length of the spring at the beginning of the video was set to 0.7, and the position at each frame was tracked, and it generated a position versus time graph to the right. And then this is how we calculated the initial conditions from before. So we know that t is equal to 2 pi times the square root of m over k. So from the position graph, we chose 3 periods of the same length, and we took the average of that to find t. And then from the equation, t squared is equal to 4 pi squared m over k, we were able to calculate k, which is the spring stiffness, using the t, and it was calculated to be 6.09 newtons over meters. And then by doing F net is equal to the force of the spring plus force of gravity and solving for L naught, we get L naught is equal to 0.053 meters. So this is the computational model. So the first image is just the initial conditions, which I plugged everything in. And the second part is also the initial conditions, in which it's the spring constant and the relaxed length of the spring, which was calculated in the slide before. And then we calculated the vector L, which basically shows which direction the spring is pointing into. And then we changed K, UG, and US to the formulas mentioned before to calculate the kinetic energy, the gravitational potential energy, and the potential energy of the spring. And then we did total energy is equal to K plus UG plus US. And this is another part. This is the while loop. So I changed the time to less than 9.972 seconds because that's the length of the video. And we set the initial energies to what it is. And then we changed the ball's velocity and position to the velocity and position update formula respectively. And then we changed the spring, the direction of the spring, which is L hat, as you can see there. And then we recalculated K, and then we found delta K by doing K final minus K initial. And we did that for UG and US as well, and total energy as well. So this is the two models graphed on the same graph, with the blue one being the model and the red one being the experiment. So some of the possible errors was that the position was tracked by eyeballing the center of the mass, which could be inaccurate. And also in reality, the system is not actually isolated from the surroundings, which means that there would actually be work done from the surroundings. So what does it mean? So is the energy principle satisfied? Yes, it is satisfied. So as you can see in the graph on the bottom right, the total energy, which is orange, is constantly at zero, although there's like change in each type of energy, like kinetic energy and gravitational energy. But this is because there's no external forces that affect the system. So the total change in energy is always at zero. And so the what does it mean part two is said to make two separate estimations of oscillation periods. So I did it using the same method as the first one, which I basically, except I did the x direction graph and the y direction graph. And so basically choosing different directions results in changes in the period, which changes the spring constant K, and thus the graphs resulting as well.